you, everyone. So, last time we started off with this question. If you take a topological space, you extract its category of sheaves, to what extent you can reconstruct that topological space? And the answer that we came to was that, well, you can certainly reconstruct the lattice of opens of that topological space by looking at what we were calling the -1 truncated objects, or the sub-objects of the terminal object of that topos of sheaves. We talked a little bit about what topoi are, and we determined that the conditions to be a topos to force the subterminal objects, these objects that are -1 truncated, it forces them to kind of look structurally like the lattice of open sets of a topological space. That was our theorem. And I suggested that what we would do now is we would start to change the categories of sheaves that we would talk about. We might talk about fewer sheaves and see what that kind of reconstructs for us. But before I get into that, first of all, I have to ask the same question that I always ask, which is, what questions do you have? When I teach early courses, I ask that question, and then I stare awkwardly at the audience. I feel uncomfortable and ask a question. I won't do that to you.
They don't ask questions. You have to ask a question to them.
I did. That was a question.
Oh no.
Let me actually say one more thing about this business with the subterminal objects. So let's just agree now that if X is now a topos, and remember, by topos I really mean infinity topos. So you've got this is a presentable category with this descent condition. And the -1 truncated objects, I'm going to think of those as opens, right? That's the game we're playing. So an object here like this is what we'll call an open in our subtopos. And when you have one of these, something kind of neat happens. And I want to kind of talk about this sort of neat thing that happens. So you can look at the over category over this object. That over category has a forgetful functor to X itself. This is just the thing that forgets that. It turns out it's fully faithful, which is why I wrote that little hook on the end of it. The full faithfulness is a consequence of the -1 truncatedness. You can check that for yourselves. It's true. This functor I'm actually going to call J lower shriek for reasons that may or may not emerge. But that's the name that I'm going to give it. This thing has a right adjoint, which I shall call J upper star. And that right adjoint has a further right adjoint, which I'll call J lower star. J upper star, what does it do? Well, it just takes an object and crosses it with U. Not you. And J lower star, well, what is that? That's something like a kind of relative sheaf of sections kind of construction. It's a certain kind of internal Hom that you have in this category. It's sort of a relative internal Hom. So you've got this sort of pleasant adjunction here. So this thing is again a topos. If you have a topos and you slice it over an object, it's again a topos. That's a thing you can check. So this is a topos, and it's a subtopos of this topos. And we want to think of this as an open subtopos. And well, you might start to think, well, hey, that's cool and everything. But in topology, I also have closed. Yes.
Sorry, maybe I should have asked this during your opening questions comment, but let's say I'm comfortable with sheaves on a space being a topos.
Yeah.
What other okay, we've made this generalization to thinking about other topoi.
Yeah, you're right.
That's the example I should have in mind.
I'm being kind of crappy, aren't I, by not actually giving you other examples of topoi. So let's pause. Oh, good point. Let's put a pin in this and let's come back to this. So let me try and tell you some other examples of topoi that you might feel good about. So here's one example of topoi of a topos that you might feel good about. So as you pointed out, of course, I can look at sheaves on a topological space. More generally, I can look at sheaves on any Grothendieck site. Right, so a Grothendieck site, I don't want to give you a definition of this because it would take us kind of too far afield, but a Grothendieck site is it's a category, and that category will have what's called a Grothendieck topology. The Grothendieck topology just basically tells you what it means for things to be open covers. And those things have to behave in a certain way so that you can actually, and so the classic example of this, by the way, is if you've got a scheme X, then there's what's called the Atoll site of the scheme. And again, I will actually give you a different way of thinking about the topos attached to the Atoll site. So I'm not going to tell you precisely what the Atoll site is unless you really insist. But the basic idea is the following. The basic idea is that the objects of this category are what are called Atoll maps down to X. Atoll maps are basically composites of covering spaces, things that function like covering spaces in algebraic geometry, and open inclusions. So these are things that are like, you can think of this as something like a covering space of an open subset of X. That's roughly what that is. The maps are what you think they are. They're maps over X. And then covering really means what you think. Like if I have a family of these things, then I can, yeah, maybe I'll say it like this. This family covers X if and only if spec of X is equal to the union of the images of spec of these, X is equal to the union of the images of these maps. So covering really means like what you think covering ought to mean. So anytime you have one of these Grothendieck topologies, you can talk about sheaves. It's kind of like a relatively minimal set of axioms to write down the notion of a sheaf. That's all you're really doing. And so all of those categories of sheaves, like the Atoll topos, to do this little game where the site I write upstairs and the topos I write downstairs. This is not universal. It's just what I do. And these things are all examples of topoi. Of course, a particular example of this sort of phenomenon is where I take just the trivial topology, in which case the category of sheaves I'm looking at is just the category of pre-sheaves. And now let me make a slightly technical comment. So we talked last time that not every topos in our sense is actually the topos of sheaves on a site. It's a little bit awkward. It's true for one topoi, but it's not true for infinity topoi, or at least we don't think that it's true for infinity topoi. And in any case, if it is true, it's not true in a good way. So, so another place where you can get topoi is by taking something like the category of sheaves and doing a process like hypercompletion. So I don't want to get into that, but there's this kind of question about, say this in a way that's helpful. I don't want to go down this road too far. So one of the things that happens in topological spaces is if you're trying to work out whether or not a map is an equivalence, you can look at all the truncations, and if all the truncations are equivalences, then the map itself is an equivalence, right? That actually isn't true in every topos. So there's this issue that not every topos has this kind of hypercompleteness property. And so that actually kind of creates a little bit of strangeness in some of the statements of things. And so that's a technical point, but it is another example of a place where you can get topoi. Please.
So another way of thinking about this is in one topo theory, like sheaves on a topological space, you can always check isomorphisms on stocks.
Yeah.
In higher topos theory, even for topological spaces, that is not true. And it's basically never true for these Atoll topoi. And then in forcing it to be true, you get another topos, which is called the hypercompletion.
Did everybody hear that? Okay. That's what I should have said. So. Yeah, thank you. Other questions about this? This is just a stockpile of examples. I will actually try to tell you a different story about this topos, a completely different story about where this topos comes from, but I'll come back. Okay, so open topoi, there we go. Open subtopoi. And so you can ask, well, okay, I like open things well enough. So is there a closed complement? Is there a meaningful closed complement? And I'm not sure if this is the best notation that I could come up with, but I always like to write the closed complement like that, like x minus u kind of thing. I don't know, maybe it's a little confusing, but I like it. And so what can you do? Well, you can look at the collection. So this is the full subcategory of those sheaves F, such that if I product them with U, I'm just going to get U. This is a subcategory of X,
Which is the terminal object.
which is the terminal object here. That's exactly right. So thank you very much. So what that means that I'm doing here is that I'm looking, as it were, at the kernel of this functor J upper star. Right, I'm looking at the kernel of this functor J upper star. And so now, this is the functor that I, yes, this is the functor that I wish to call I lower star. And this thing has a left adjoint, which I will call I upper star. By the way, this is a, yeah,
If V is another if V is another open, then what
Yeah.
is V cross U?
yeah,
Is it G open V intersection with U?
yeah, that's right. That's right. So if you take the product of two opens, right, then that product really functions like an intersection.
I'm surprised the condition is F cross U is U and that F cross U is empty or true.
It's that you're getting really exactly the terminal object in this category here. Yeah, this is the,
So if V is different from U,
let me, here's the example that you should bear in mind. So here's the test example that you can sort of do this with. So take an open of your favorite topological space, right? And then ask yourself what this is. So if script dx is sheaves on your favorite topological space and U is an open inside X, and I do this game, right? So we know that we can look at X sliced over U, X, and then this funny complement, and you can ask what these things are. If you ask what these things are, then on this side, you're getting exactly sheaves on U. Right? This is sheaves on X. And on this side, you're exactly getting sheaves on Z, where Z is the closed complement of X. So that's the exercise to check that this is a reasonable definition. It's true. So, so what? Well, so something interesting happens here. Oh, by the way, let me just set some notation out and tell you that if you violate this notation, penalties will ensue. Opens are denoted by J, and closed are denoted by I. You will be banished from the club if you violate this rule. Okay, so what is this situation? What's happening here? Well, something kind of cool is happening here. This is an example of something called a recollement of categories. So what is a recollement of categories? It's the following situation. Yeah, it's the following situation. So you've got a category that you like. Maybe I'll call this C. And you have a category that I want to think of as the category attached to some open. And you've got another category which I want to think of as the category attached to some closed. These are going to be full subcategories of C, like that. And they're going to have the following properties. First of all, this thing is going to have a left exact left adjoint. This I will call J lower star. This is going to have a left exact left adjoint, which is J upper star. And this is going to have a right adjoint. This is going to be left exact, and it's going to have a right adjoint. Yes, sorry. Left adjoint. Thank you. It's also got a left exact left adjoint. Thank you. Like that. Not to the place where this has the other, when I stabilize, I'll have the other adjoint, but I'm not there yet.
The directions be different.
Probably.
First star should go in now.
Yeah, thank you. J upper star, J lower star, I lower star, I upper star. Now it looks right. Sorry. These Z mod 2 actions are going to keep happening. I'm sorry. That's why I have to be so careful about saying that I and J are as they are. That I is closed and J is open. It must be this way. Okay, so what do we have here? So we have that I lower star and J lower star are fully faithful. That I upper star and J upper star are left exact left adjoints. So not only are they left adjoints, but they preserve all finite limits. That's, we're going to assume that these categories have all finite limits in order to make this story go. And then let's see, what else do I want to say? Well, I also want to say that that if you look at the functor from C to CU cross CZ given by I upper star, J upper star, that this is conservative. So in other words, if you're trying to work out whether or not something in C is an equivalence, it's enough to restrict it to CU and to CZ and CZ, sorry, and ask whether you have equivalences there. So this situation is called a raccourcissement. And what's it for? Well, it's for the following. Let's say I want to write down an object of C. So let's say I want to give you an object of C. What do I have to do to give it to you? Well, my claim is that all you have to do in order to give this object of C is give yourself an object of CU, which is actually going to secretly be J upper star of your F, and an object of CZ, which is secretly going to be I upper star of your object, and a certain gluing map. So you need to give me something on U, and you need to give me, so this is an object of CU, you need to give me an object of CZ, and you need to give me one more piece of information, which is a map from FZ to I upper star, J lower star, FU. This is the so-called gluing map. This is sometimes called Artin gluing. Yes.
Using one condition, which is the I lower star J upper star is.
Thank you. Yes, sorry. I'm so sorry. Yes, it was true here for because I defined it that way, but I didn't say it. Yes, thank you very much. Peter's right. I need another condition which says that if I do J upper star of I lower star, J upper star of I lower star, then I just get the constant functor at the point, which is definitely true here, right? I mean, I defined it that way, but I didn't say it here for part of my assumption. So these four axioms, these four axioms are what you need in order to have a raccourcissement. Thanks, Peter. This is what you need in order to have a raccourcissement. And in that circumstance, when you have these four axioms, then what I'm telling you is that an object of C is the same thing as an object of CU, an object of CZ, and a map like this. Okay, well, how does that work? Let me show you. Erasers. How do I reconstruct F from this kind of information is the question.
We don't have to say too precisely, but what are you assuming about the category other than what you wrote?
So I'm just assuming right now, I'm just assuming that these categories are, they have all finite limits. I don't need to assume anything else. So they have a terminal object, which means that this makes sense. And they have finite limits, so this left exactness makes sense. And that's all I'm asking for. The examples to which I'm going to apply this are the topos, which have all that stuff and a whole lot more. and stable infinity categories, in which case you actually get some other adjoints in this picture, but I'll come to that. So in particular, when you define a recoulement, you don't actually insist on the presence of this J lower Schrieg functor, which is kind of weird because that was the easy one to write down. Like of all the functors that we wrote down, that was the one I had to explain the least, right? But such is life. Okay, so if I have an FU and FZ, that's a really offensive thing to say, sorry. If I have an FU and FZ and a phi, then how do I reconstruct a single object? That's a question that you can ask. And here's how you do it. So I take this map. This is a map that goes from FZ to I upper star, J lower star of FU. And the first thing I'm going to do is I'm going to I lower star that map. First thing I'm going to do is I'm going to I lower star that map. And well, here here I have I lower star, I upper star, and I know something that maps into I lower star, I upper star because I have the unit for the adjunction, excuse me, which comes from J lower star FU. So now if I take the fiber product of these two things, then I get an object. And the claim is that every object is uniquely determined by such information. So what am I doing when I do this? What I'm really doing is I'm setting up an equivalence of categories between C itself and a kind of oriented fiber product of CU and CZ. So I'm setting up an equivalence of categories between C and, well, I'm going to write this kind of crazy looking notation. Category theorists call this a comma object. I've never understood why there's no commas in sight. What is it for? Why are they called comma objects?
It's like the bar construction.
Yeah, what's the bar construction all
Apparently,
about?
people used to denote it with with some bars, and that's why I mean, this is terrible.
My center is named after someone.
It's not actually named after some.
It's not named after my yeah, naming things after notation is bad. It's just a dumb thing to do. Anyway, so okay, I'm gonna stop moaning. So what's happening here? So we've got you're trying to make a fiber product, but you just don't really finish. So it's almost a fiber product like this. Which way does the two morphism go? Oh my God. Come on, Barwick. I think it's down. Do you agree, Peter?
Wait. No, it's the other one.
I knew I was gonna get it wrong.
It's because it's the oriented push out in topoid.
I know. Yeah, okay, it goes that way. It goes that way. So it's the universal thing that makes this diagram kind of commute with this two morphism, right? So if I had another thing with the two morphism in, then it would map to that in a unique way, blah, 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 blah. But at an explicit level, like when you just write down what the objects are, what are they? Well, they're an object here, and a comparison map, which isn't invertible anymore, that happens down here. Right, so there's your FZ, there's your FU, and the comparison map is exactly this gluing map phi here. All right, so this is the recoulement type situation. Now,
You were claiming that C is equivalent to that.
I am saying that C is equivalent to that. Thank you very much. Thank you for getting me back on track. Thank you. I'm claiming that C is equivalent to that. So why is that important? Why do I care about that? Well, I care about that because categories are complicated. If you hand me a crazy category, I might want to try and break it down into simpler pieces. This is giving me a way to do that. This is giving me a way to take my complicated category and break it up into smaller pieces. And what we're seeing is that, in a sense, what's happening when you play with these opens in a topos is that you're taking your complicated topos and you're breaking it up into simpler pieces. So there's a sense in which you're taking a category, in this case a topos, but we'll be more general in a moment. You're taking a category and you're trying to break it into simple pieces, and you're doing that using the geometry of the situation. That's the principle that I really want to get at here. Yeah.
Or the fact that U is minus 150.
Yeah, it's absolutely essential here because otherwise these functors aren't fully faithful. Yeah, so you don't even get off the ground if you don't have that. Yeah, thank you. Good question.
Do you have a formula for I upper star in general?
Do I have a formula for I upper star in general?
Yeah, like a description of it.
That's in terms of you. Yeah, that's a fair question. Probably shouldn't I?
So actually,
You know of one?
no, I think the only way that I know how to see this somehow directly is you notice that this whole subcategory is closed under limits because limits commute.
Yeah.
And then it's also closed under weakly contractible colimits, in particular filtered colimits. Therefore, it's
The
presentable.
left
everywhere.
adjoint exists.
Yeah.
Yeah.
But yeah, I don't think there's some explicit formula, unfortunately. I tried to use such a thing once and I could not figure it out. So
You couldn't find a formula, so no formula exists. You should have started off with that. No formula exists. Okay.
Question.
Yes, please.
Definition of an open subject. Is it always of the form slice over something open?
Yeah, that's the definition. That's the definition I'm going to use. Yeah, it feels a little stupid as a definition, doesn't it? So let me give you another definition that I could work with here. So it's a fully faithful morphism of topoi. Ignore this, Jay. So I didn't actually tell you what a morphism of topoi is. I should probably tell you what a morphism of topoi is. So a morphism of topoi is by definition an adjunction where the left adjoint is also left exact. Left adjoint needn't preserve any limits at all in general, but we're going to require, in order to be a morphism of topoi, I need F upper star to preserve finite limits. By the way, that's sort of analogous when we were thinking about morphisms of locales. Remember, I said that the morphism, that the pullback map in the morphism of locales had to preserve both unions and finite intersections. This is the sort of categorified version of that sentence. So that's what a morphism of topoi is. Now what I'm going to require is that this is not only a fully faithful morphism of topoi. So, by the way, the way it works is the morphism of topoi from X to Y. Even though the left adjoint goes this way, like there's some ambiguity there, but I always go this way. So this is a fully faithful morphism of topoi from one thing to another thing, but with the additional condition that it be what's called a tall. If you insist, I will tell you what a tall means, but there is a definition. That definition turns out to force this thing to be a slice category, basically automatically. And you get this further left adjoint for free. That's part of the definition of being a tall. So you can characterize this completely intrinsically. Is what I'm trying to say. You don't have to say, oh, it is a slice topos. It is something of this form. You can characterize it intrinsically. But what you end up with is equivalent to saying that you've sliced over a -1 truncated object. So might as well start there. Yeah.
The polymorphism of topo is always slicing over a -1 truncated object.
It's always slicing over an object. But in order to be fully faithful, that object has to be -1 truncated. Yeah. So the tall morphism is always slicing over an object, and in order for that lower star, or equivalently lower shriek, to be fully faithful, that object has to be -1 truncated. Yeah.
In algebraic geometry, there is this characterization of the tall where one condition or part of the condition is that sort of the diagonal map is the inclusion of a path component or a connected component. Is
there an analogous thing here?
Is that the same? Does that also hold for topoi?
No, it doesn't. Okay. I'm trying to think if I understand how to make that. I know
how to phrase it. I wouldn't know how to phrase it exactly.
I don't think I do either.
I don't know if you can talk about connected components of topos.
I mean, you totally can, but I think I have something. I don't think I have an appropriate analogy for that concept in my head. Interesting question, actually. There's a little bit of a fraught thing there, by the way. I'll just mention this as a sidebar. You know, taking products of topoi is a weird thing to do. To a certain extent. I mean, like the product in the category of topoi is the tensor product in the Lurie tensor product of presentable categories on the corresponding side. But a lot of the stuff that you might ask for, like, you know, the diagonals to be, you know, immersions of various sorts, all that stuff is kind of, it starts to break down a little bit at this genera. There's some funny business there that you have to be cautious. Maybe that's a vague comment, but it's true. Other questions before I move on? Yeah.
A fairly historical question, but maybe that's a relief on it. But this equivalence, I presume, at this point is completely formal, right? With your
Utterly formal, yeah.
Understood. If recogma, I assume first appears in the homology business in the 1960s.
Yeah, it's an SJ4.
It doesn't look entirely formal when they did it. You know, when somebody he distilled all the formal essence of it. It didn't look, at least I remember it not looking terribly formal.
Yeah, I remember also in like Milton's book, at least when I first read about it. It was not somehow obvious to me that it was formal, but then at some point.
No, it takes quite a bit of work, I think, to turn it into a completely formal statement when
Yeah.
Milton is doing it or any of it.
Yeah.
Interesting point. You know, I hadn't thought about that. I mean, I haven't looked at
This
SGA4.
is why I admire homotopy theorists, by the way. But
Paper of Wraith or something from maybe the 70s where remember him say like somehow explaining why this is I don't know what who first did this.
But
Gavin Wraith, I think.
But there's some, what are the notes that Arthur wrote about?
Oh, these like sites and the Harvard notes.
Yeah, and the Harvard notes. Yeah, exactly.
He explained
That's like 69, and I swear it's completely
right?
formal in
maybe I'm just remembering. Yeah, maybe it's fine.
And that's why I think people started calling it, I thought that was why people started calling it art and gluing, but maybe misremembering. No, I mean, that's a fair point. I mean, yeah, I mean, some of this stuff, there is a kind of distillation that's happened here before I started talking to you, right? I had the whole history of mathematics before I started. But it's true. I mean, you're right. I mean, I remember in Milne, I didn't remember that about SGA4, but I do remember that in Milne, he kind of really makes a meal out of this, but it's not that deep. I mean, it's, you know.
For example, I think we may even have stocks and things like that.
Is the point if you're working in a category of sheaves, you cannot do this object-wise kind of? Is that like?
I think that's part of the issue, yeah, is that you use the crutches that you've got if you're sort of relying on the fact that you know that you're working with sheaves and you can use stalks and stuff like that, just as you say. But that's a really good point. I hadn't thought about that. That's a good point. This principle is something that I really want to hang on to. This idea that what geometry is really trying to do for us, especially when we try to think about something like the geometry of higher categories, which is sort of where I'm trying to point us to. What is that geometry doing for you? It's really trying to break up your category into the simplest pieces that you possibly can. We're trying to break up your category into the simplest pieces you possibly can. And well, let me actually take a quick detour, since I'm already talking about recoulement. Let me take a quick detour and say something about the stable situation. Because one of the things that happens is that we're interested in being able to do this kind of thing when maybe you don't have a category that came from a topos in an obvious way anymore, and maybe you just it approached you as a stable infinity category. So for example, maybe someone handed you the category of spectra and said, all right, break this up into the simplest pieces you possibly can, please. And then you started working really hard to figure out how to do that. So in that circumstance, so if A is a stable infinity category, then when you're in this recoulement type situation, you have even more structure lying around that you can kind of stare at and enjoy. So namely, if I'm in this Recollement type situation, then I have a little bit more symmetry. I have this J upper star, I have J lower shriek, I have J lower star, I have this triple of adjoints, but I also have a triple of adjoints on this other side. Namely, I have I upper star, I lower star, and a further right adjoint I upper shriek. That's only because, well, I guess I always have this when I've got a zero object. Is that all I need at this point? Yeah, a zero object I always have.
However, shriek, you need an initial object to get, and then if you want both, you need a zero.
Ah, okay. So Peter tells me that if I want J lower shriek, then I need to have an initial object in A, and if I want I upper shriek, then I need to have a zero object in A, an object that's both initial and terminal. By the way, I should have asked, are people cool with stable infinity categories? Do we know? Cool.
I'm not, so you don't have to spend time on me.
You can shift and you can shift back.
I have
So
the
like
general
conferences
ideas
and stuff like that. So if you take suspension and loops, you get back to where you started. And the other way around too. Okay, we'll talk more. Okay, so in this sort of stable situation here, we have this kind of very pleasant circumstance. I really like thinking about this. I mean, you know, these sequences, each of these three exact sequences is each of these three sequences, you know, J lower shriek, I upper star, J upper star of I lower star, and then this one, they're like short exact sequences, right? This is exactly the kernel that you get by taking A and quotienting by the image of A, this map here and so forth. All of these things are sort of short exact sequences. And so you have a bunch of really nice looking, this box here gives you a bunch of exact triangles that you can think about. So for example, if I have an object F of A, then I can look at I lower star, I upper star of F. Like, let me actually match what I did there. Let me try and match what I did there. So let me do J lower star, J upper star of F. That also maps to I lower star, I upper star of F. And then the corner here, I have I lower star, I upper star, J lower star, J upper star, F. And this is a pullback square, which is also a push out square because I'm stable, Cartesian square. And well, what's the kernel of this map here with a fiber of this map here? It's exactly I lower star, I upper shriek of F. And this one is J lower shriek of J upper star of F. And well, I guess I could fill this out even further. I felt like it. So this is actually equal to I lower star, I F. Now every square is both a pullback. Sorry. Anyway, I'll just leave it like this. The rows and columns are all fiber sequences.
in the top left.
Sorry, this is J lower shriek, J upper star of F.
The left.
Oh, that's a zero.
That's a zero.
That's a zero. I don't know why I put it there. I was just having fun. I wanted each row and each column to be a fiber sequence. That's what I was trying to do. Yeah.
So you said that all of these three sequences are exact. So is it true that any of these six functors determines the whole recoulement?
Yeah, that's right. That's right. That's exactly right. Yeah, you only need one to get started, and once you can build them all out. Exactly. Assuming it has all the right properties. Right?
If it belongs to a recoulement.
If it belongs to a recoulement, it can be reconstructed. Exactly. So by the way, I mean, for those of you who think like things like chromatic homotopy theory, the usual square that you get, whatever they call it, the chromatic bluing square, that's one of these. It comes exactly from a Récolliment. So you see the principle here is that I want to try to understand a geometry attached to things like symmetric monoidal categories that will allow me to break up my complicated category, like the category of spectra, into simpler pieces. And I'm using as a guide for that sort of thing my experience with Topoi, where I had this breakdown. Okay, how am I doing? I started at 9:30 pretty promptly, right?
A little bit after, like 2 minutes after.
All right, so I promised that I would start talking about locally constant sheaves, and then I got distracted because I was telling you fun stuff about Récolliment. But let me go back now to locally constant sheaves, because I want to kind of amp up this story a little bit. And the way I want to amp up this story is the following. I said that you want to sort of break down complicated categories into simple categories. And what we see here is a way to do that, but it sort of only breaks it down in terms of opens and closed, in terms of this Récolliment business. Can I get finer breakdowns is a question that you can ask. So let's try to answer that question. And so to answer that question, I'm going to start in a totally different place. I don't know if it's good style to, like, in the last 15 minutes of a talk, just like completely introduce a new topic, but here we go. Here's a manifold. Manifold M. And here's a point on that manifold, little x. And I've decided that I'm interested in locally constant sheaves on this manifold. Actually, let's assume this is a connected manifold, just so I can tell a good story here. And I decide that I'm interested in locally constant sheaves on this manifold. So what does that mean? That means that this manifold admits an open covering, and for each piece of that open covering, the sheaves that I'm interested in are, I'm saying that in the bad way. For a locally constant sheaf is one such that there exists an open covering of the manifold, such that the restriction of that sheaf to each of those open pieces is a constant sheaf. Real boring. Okay, so here I am at home on my manifold. I'm going to go, I have a locally constant sheaf living over this manifold, which I will denote thus. And I'm going to start here at home, and I'm going to go for a drive. Okay, so I'm going to go for a drive or a walk or whatever. But as I do this drive, I'm going to keep my arm out the window, and I'm going to hold in my hand a section of this sheaf. I'm going to keep in mind an element of the stalk over this point. And as I drive, I'm going to drive this way. And as I drive, I'm going to watch what happens to that stalk. I can do that because I can take this loop that I'm going to come back home when I'm done. When I come back home, I will have a compact set. And so I have a finite collection of opens. And on each of those opens, I can arrange for those opens for the sheaf to be constant on those opens. And so I can really genuinely transport my section as I drive around. So I'll do that. When I do that, what I discover is that I'll have a different section when I get back. How will it be different? Well, it will depend on what kind of loop I took, right? If my loop was contractible, it actually won't be different at all. So I'm not very good at drawing manifolds. So I'm not nearly as good as Luke at drawing manifolds. So this particular example is not an interesting loop, but nevertheless. What's that?
Only good at singular ones, not
Oh, you can only do smooth. Okay. There you go. That's the secret. So I just need to introduce some singularities, and then I'll.
This one looks plenty singular.
Okay, fair enough. Okay. So what does that mean that I'm looking at here? Well, that means that I'm looking at given this point, what can I do? Well, for every single loop, I can look at the action of the pi1 on this stalk. So I get, how do I say this? I get a, I'm just gonna write it like this. I get a functor into spaces, because I'm talking about sheaves of spaces at the moment. I don't have to be, but I can. I get a functor like this. Actually, now that I've written it that way, I'm kind of being a little dopey by demanding that I be connected. So I could have just written a big capital pi and said the groupoid. And now I can actually remove my dependence on X as well. Okay, fine. But the point is that this isn't quite an equivalence of categories if my target is spaces. If my target were something like vector spaces, so if I was talking about locally constant sheaves of vector spaces, then this would be an equivalence of categories, and this would be something called the monodromy theorem. Right? And it says that locally constant sheaves are just representations of your fundamental group. If I want to be fancier about it, and I want to talk about these more impressive locally constant sheaves that we've been talking about, valued, I'll be cool and write anima. Then what do I have to give you here? Well, I have to give you the entire homotopy type of M regarded as an infinity groupoid. And now this is an equivalence of categories. So you don't just have the loops anymore, but you also have all the higher homotopical information.
Is this statement in Lurie somewhere or where?
Yeah, so this statement is, so the first place I know this statement is written down in a way that's actually proved is in Toen. Although not able to, does anyone know a precise reference? I know it's in something that Toen wrote in like.
Yeah, that's fine. I can.
But then this statement is also in Lurie's. Is it in higher topos theory?
8.1.
Thank you, Peter.
Maybe it's 8.2.
Oh, okay.
But well, it's kind of 1 and 2.
So this is a sort of very fancy version of the monopy. By the way, you could use this if you ever teach homotopy theory. This is a way that you could go about it, right? What you could do is you could say, well, what is the homotopy type of a manifold? Well, what you can do is you can look at the following functor from infinity categories to infinity categories. And what'll it do? It'll take your favorite infinity category and it will spit out locally constant sheaves on M with values in your infinity category. Maybe I need to say, no, that's good. This functor is representable, and the representing object is the homotopy type.
So you can define what an infinity category is without ever saying what a homotopy type is?
There's some pedagogical questions about this approach, but it is a valid, reasonable way to think about things. I'm not sure what your teaching reviews will be like after you say those, but.
Or you can do the Mark Waugh approach, where he gave his introductory lecture in Regensburg saying anima is an irreducible concept. It's amazing to read these notes, and then he gets to the Bloch-Kato conjecture. He starts with this, though.
What a legend. Okay, so this is a completely different way of thinking about homotopy types from the way that we grew up with, right? I mean, it's certainly different from the way I grew up with. You're all younger than me, so maybe you saw this first, but this is a strange way to think about homotopy types, but I really like it, and I want to now carry it over into as many other contexts as I possibly can. So the first place that I want to carry this over into is into the universe of schemes. Be a little careful about my time here. First place I want to carry this over to is into the universe of schemes. So I'm interested in circumstances where I've got a nice scheme. And well, I want to talk about locally constant sheaves. And one of the things that's sort of the motivation for this Étale topology business is the fact that if you think of local constancy as local with respect to the Zariski topology, you're going to have a bad time, right? Because local constancy and because the open sets in the Zariski topology are far too big. This is a very coarse topology. So asking for local constancy there is just not the right thing to do. So you need to ask for a finer topology, but you can't ask for the finer topology by using subsets of your scheme. Instead, you have to do this thing where you pass to covers. You have to pass to these étale covers that I was describing before. So what you do is you say, all right, well, hey, I'm interested in locally constant sheaves for the étale site of X. And then you ask a question, and the question is, and you know, once again, I can kind of insert a variable here, which is the category in which my sheaves are going to be valued. And then you can ask the question, well, is that functor that you get representable? And the answer is no, not really, not exactly. It's not representable. It's almost representable, but it's not quite representable. It's pro-representable. So this functor turns out to be pro-representable. Let me do a quick example just to emphasize how this goes. And then maybe I'll stop because I don't want to, I want to tell this story again next time in a little more detail. So I will come back to all this if I'm moving too fast right now. But let's just think about the circumstance where X is spec K. So we think about locally constant sheaves for the étale topology on spec K. Well, what are étale covers of spec K? Well, they're just the separable field extensions and, well, coproducts of spec of separable field extensions, stuff like that. So when I think about locally constant sheaves, what am I talking about? I'm talking about sheaves that are trivialized. What's a sheaf? A sheaf is just, you know, well, I have to, for every separable field extension, I have to give you a value of your sheaf on that separable field extension, right? And then at some point, that becomes locally constant. And so the question is, what are locally constant sheaves on this thing? With the étale topology. Let's do again anima. If you do it for anima, you can do it for anything. Well, they're just spaces with an action of the absolute Galois group of K. But the absolute Galois group of K isn't just a group, right? It's a profinite group. So what I want to say here is I want to say functors from the classifying space of the absolute Galois group into anima. And I can almost say that, except I have to say something about the topology that I have on the group. Right? This is a profinite group. It means that it's got a topology. It's what's called a stone space. Right? And so, you know, it's a compact Hausdorff totally disconnected topological space with a group structure that's where the group map is continuous. And so I really want to be able to talk about the continuity of the action on here. So I want to be able to say continuous functors from here to here. This is a good place for a cliffhanger. How am I going to say that? I'll try and answer next time.